Hey everyone, happy Friday, and welcome back to another episode of Get Your Tech On. This is actually episode number 104, the show where we dive deep into all things DOCSIS and cable tech. I'm Brady Volpe, and joining me, as always, is the legendary John Downey. Today we're taking a close look at a must-read industry reference from the SCTE and Cable Labs called Understanding and Troubleshooting Cable Upstream RF Spectrum, also known as SCTE 294 2024 R1. Trust me, this document's pure gold for anyone looking to level up their upstream troubleshooting game. We'll kick things off with a breakdown of two-way operation covering why signals flow differently going downstream versus upstream, why reverse funneling can make or break your network performance. Next, we're going to dive into the nitty-gritty of diagnosing noise and ingress, discussing common culprits like impulse noise, RF interference, and drop amps. And finally, we're going to wrap things up by looking at some troubleshooting concepts in the SCTE 294 document and provide details on how to access the document. So be sure to stay to the end of the show so you know where you can get a copy of this awesome doc. So this is going to be a jam-packed session, so stick around because it's going to be legendary, just like John. Speaking of him, John, how have you been, man?
Good, good. It's yesterday was the equinox, so first day of spring. My chickens are producing more eggs because they got more sunlight. So the egg production is going good. The avian flu and all that's not affecting me, which is a good
Well, it's
thing.
good to hear. And we saw one of your little peeps pre-show. Too bad all the rest of the audience doesn't get to see one of your little peeps.
Yeah, we start hatching some of our own after a while just to and we see what we get. But this time of year, I let mine free range, and sometimes the hawk will come down and pick off a couple. So I got
Well, hawks
to
need to eat
replenish
too.
Yeah, it's a circle of life around here.
That's right. That's right. So let's kick things off. One of the first things we'll talk about before we get into the SCTE 294 paper was last week. I was at the SCTE Cable Labs Winter Conference 2025. I'll just show a screenshot of basically. Pretty much, this is really all we can show because the Cable Labs Winter Conference is a NDA show, a non-disclosure agreement show. So for those that attend, we're really not supposed to talk about the things that happen there. It's for members and vendors only. But I want to highlight just kind of the theme of the show, which was reliability and quality. Everyone kind of is at the point right now, most operators are at the point is we have the speed for cable operators. DOCSIS 3.1 and now DOCSIS 4.0 that's being rolled out. In fact, there are 3 bucket trucks outside of my house right now. They're upgrading the analog fiber node to an FDX fiber node. So I was talking to them as they're doing that install. And so for those of you that know, DOCSIS 4.0 is part of that FDX rollout. So that is a DOCSIS 4.0 fiber node that they are installing outside of my house. DOCSIS 4.0 is real. It's being deployed. That means even more speed. So speed is not the issue. It is reliability and quality. And that was the big theme at the Cable Labs Winter Conference that everyone was really focused on. How do we do that? What's the means? What are the capabilities? And software analysis and different tools, smart amplifiers, proactive network maintenance, profile management application were all big talks, along with AI. AI was a huge theme at the show. We have lots of software, but we're going to need smarter intelligence to wrap around that software in order to make our networks more reliable and improve the quality of our networks. So it was a great conference. I definitely recommend anyone who's able to attend next year's Cable Labs Winter Conference, which instead of being in Florida is going to be in Denver. It's going to be somewhere in Colorado. I don't know if it'll be in Denver, and it's going to be a little later in the year. It's an excellent conference to attend. It's a very technical conference, and it gives you a lot of insight of not only what's happening now, but where the cable industry is moving in the upcoming years. So, great conference to attend.
Yeah, I attended it a few years back, and it's a nice place to go, and there's a lot of people there, a lot of talks. I like the fireside chats because they're more interactive and more dynamic, I guess you could say. You know how like you get into a big room with someone speaking, the doldrums about it, it start dazing off. But the fireside chats are right to the point, unlike me. That's not too long, but they're right to the point, and it's like, okay, and you have more interaction and stuff, smaller, more intimate, I guess you could say.
Yes.
So I always enjoyed them, and they were always pretty good. You mentioned it's like we keep using that term like cable show, cable this, and didn't SCTE take that word out of the expo?
Yeah, it was
Like
this past year. It was cable.
Tech Expo.
Yeah, it was Tech Expo. They took the cable out of it, which I still am struggling to not say. I want to say Cable Tech Expo because we've called it that for ever since I've been in the industry, and even before me being in the industry. But yes, it is Tech Expo. I think we're all really, we know as an industry, we're more than just cable. I mean, we're cable, we're fiber. Many operators are doing wireless, or they're doing telephony as well. So we convergence is another word that's very popular in industry because we are much more than just cable. So I think that's the big push to get. We're not just cable anymore. We're well beyond just cable.
Your point about speeds, we got the technology for the speeds, and now you see he's talking about quality, but it's quality of experience too, right? Not just quality, but how the end user perceives that quality.
Yes.
And reliability and availability, they're not quite the same thing. Ron had a nice paper on reliability, 5 nines, availability.
Yes.
So there is a slight nuance there. But to know that it'll be there when I need it, it's not going to go up and down, and that's reliability, like how many times it goes offline, online, because that's a big nuisance. So knowing that I can rely on my network to be there when I need it and the speed I need, and then so the quality of experience. So I think that's critical, and I think security as well. Like just as end users, we get tired of spam or information we don't know it's correct or not. So it's like the more information that's force fed to us, it's like, can AI help us discern what is real, what isn't real?
Yes.
But AI is also contributing to it. There's AI characters online that we don't know if they're real people.
Well, and there were a couple of sessions on security, and one thing, DOCSIS 4.0 adds a number of additional layers of security over previous versions of DOCSIS. So not only, with previous versions of DOCSIS, the communications between the modem and the CMTS are encrypted, and the modem must authenticate itself with a CMTS. The modem must say, I'm a DOCSIS authenticated modem. I have some encryption in me, but now with DOCSIS 4.0, the CMTS must also authenticate itself with a modem. So we have two-way authentication now, and that we're just continuously increasing that security to make sure that we have two-way. Just like we hear on apps like WhatsApp and Signal and some of these where it's two-way authentication. That same thing is being put into DOCSIS. So we have just more security in our networks, and we need it. We need it. To your point, AI. People with AI have a lot more ability to hack us. There's a lot of discussion. There's like we will be hacked in 2025 as individuals because of AI. So we need that reliability and that security in our networks. So with that, John, let's get into our paper, SCTE 294. This is a paper that we at Cable Labs and also SCTE have been working on. Took us about a year to work on this paper. A number of authors participated in it, myself included. And this one focuses on the upstream. So, about 6 months ago, I think, John, you and I did a video on SCTE 280, which focused on the downstream and looking at downstream impairments, particularly focused on full band capture. This is basically the brother or sister to that SCTE 280 paper. This focuses on troubleshooting the upstream. And I want to pull up the table of contents for this because we don't have hours and hours and hours to go through this, but there are a few sections today that I wanted to highlight for our viewers. And also, I see in the chat room, we already have Mr. Freeze. Good to see you, Mr. Freeze. So feel free, folks, in the chat room to ask questions as we go along here. We'll try to do our best to address them. I encourage everyone to download SC294. Again, like I said at the end, I'll have a link for that, but you can Google it and also find it easily. This is a freely available paper for everyone to download, but it has lots of great information for it. We can only cover some highlights today. And I want to start off with one that I think it's really, really importantly for everyone to understand reverse noise funneling in the cable plant. And so I'll just read here a couple sections I've highlighted. Figure 2 graphically illustrates, and I wanted to do this for, because I was talking at Winter Conference, there are still some people that all they do is listen to the audio version here. So I want to try to make sure that I do a better job for my audio listeners of highlighting what I'm showing on the slides here. So here's to my audio listeners. Figure 2, which I'm showing on the screen, graphically illustrates upstream operations, signals coming from subscribers in different parts of the node service area, which are indicated in blue, green, and red arrows, travel upstream towards the node. The intended signals operate with grants using frequency division multiplexing and or time division multiplexing, so that at any one point in time and frequency, only one intended signal is present. And what we're showing on the image below is we have 3 different upstreams coming into the fiber node. One upstream is highlighted in blue, one upstream is highlighted in green, and a different upstream coming into fiber node is highlighted in red. And then after the fiber node, this would be on the fiber going into the head end, we're showing that the blue, the red, and the green upstreams are all combined together. And that is the concept of funneling in the return, that all those upstreams get combined together. And if all the upstreams are noise-free, then all the subscribers will generally be pretty satisfied with their service. Would you agree with that, John?
Yeah, I mean, this is basic stuff, noise funneling. We talk about this 20, 30, 40 years ago, and how critical it is that even one customer with ingress could affect everybody, because
Correct.
Everybody sees the same noise floor in the head end. So CNR, carrier noise ratio, really is the same for everyone. But with that said, SNR, it's not just semantics here, signal to noise ratio could be totally different. Because when we look at MER, SNR, which are sort of the same thing when it's reported from the CMTS and cable modem, you could have things that aren't showing up in the physical layer on a spectrum analyzer. So a spectrum analyzer, I feel, is like CNR, amplitude to frequency response.
Right, because in a spectrum
MER,
analyzer, you can't see the impact of what that, a poor CNR is going to have on that, on your DOCSIS channel, on your DOCSIS communications.
You could have micro reflections, which is not going to show up on the spectrum analyzer.
Yeah.
You could have a group delay, which is not going to show up in the typical settings of your spectrum analyzer. You might need a signal, a different type of test equipment, right? But we're relying on the CMTS and cable modem to report those things, to say, my constellation of 16 QAM is not as clean as it should be, and I'm going to assign like a number to the fuzziness of that constellation, and that will be my MER/SNR. So I could have different MER/SNR readings, even though noise funneling is giving the same CNR for everybody. But it's critical to know that the noise funneling, one bad customer could affect everybody. And that's why we're trying to stay on top of it. But then also realize that because of the low frequency nature in coax, that lower frequencies, 5 to 42, 5 to 85, has less attenuation in coax. The farther you are away from the node, you would think you have more attenuation, but you don't. The tap values are usually based on the downstream level, so the taps are low, and then the coax loss is low at low frequencies. So the farther away you are, the more of an impact you can have on the upstream.
Correct.
Unless we do conditioned taps and stuff like that.
So in this next slide, we show an example of just one of the upstream legs having an impairment on it. So, and this comes from section 6.2 of SCTE 294, and it says, in both the upstream and downstream directions, there are intended signals and undesired signals, such as amplifier noise, ingress, or spurious emissions. And then figure 3 illustrates interference of some kind, shown as a lightning bolt, originating in the lower part of the node's service area. So again, in figure 3, we're showing 3 upstreams, the upstream again in blue, an upstream in green, and that third upstream in red. Only this time, that upstream in red, we show little lightning bolts on that third upstream. And the lightning bolts are to indicate that there is some noise probably originating from a single subscriber's home, or maybe a couple subscribers' home, and that noise is traversing the entire path of that upstream all the way up to the fiber node. And here is where the green, blue, and red upstreams are all combined together. And now after the fiber node, on that fiber that's, again, likely going back to the hub site or head end, we see the green upstream, the blue upstream, and the red upstream combined together, but that lightning bolt is shown impacting all 3 upstreams. So the noise that could be coming from a single subscriber's home it's not just impacting the red upstream, but because all 3 upstreams are combined together, it's also impacting the green and blue upstreams. And this is the case where a single subscriber's home on the return path can impact all 3 upstreams, or everyone that is on that upstream. So noise funneling at its finest.
And let's elaborate also. It's kind of like we're assuming that ingress is at the same frequency that you're trying to use your signal. So it funnels back and it affects that same frequency. But it could be worse than that. It could be at a different frequency, and you think, it's not lining up right underneath my QAM carrier, so it should be okay. But most of the nodes out there right now are not RPD, they're not digital, they're analog. So that ingress, if it's steady state enough power, it'll cause laser clipping.
Right.
Now with laser clipping, it doesn't matter what frequency you're transmitting at. You're getting byproducts, you're getting mixing, heterodyning of signals. So you're getting ghosting, harmonics. You're getting all kinds of other problems, right? The node's going into a non-linear type of response, which is why we say it would be better to go with digital reverse, which is typically like RPDs and stuff like that, because you don't get laser clipping in that case. Because when it's digital laser, it's just on, off. It's Ethernet. It's not the analog nodes that we know. But I bet you we're probably what do you think we're at? Like 70% analog nodes out there? 30% RPD?
It's difficult to tell because you can't look at an analog node and determine it's automatically. You can't look at a node and determine it's analog or digital. And there's, like I said, there's been a node sitting outside of my house for a while that was replaced only a couple of years ago, and I thought it was digital. Then I was talking to the guys out there today, and they're like, "No, this is an analog node. We're switching it out for FDX." And give a shout out to Trevor today there, who is it? To Sweet Lou, who said he wishes he could participate, but he's out and he's in the middle sweeping some FDX amps. Maybe he's out there at my house sweeping them now. And shout out to Trevor from PEI Canada. Trevor, glad you're catching it live. Welcome. So, but yeah, I don't know what those be some good statistics to see, because you have such a variety of cable operators across not just North America but South America, Europe, Asia. Very interesting statistics.
The other thing is, if that noise was constant, it'd be easy to troubleshoot. The problem is a lot of the upstream is like bursty.
Constant noise is so easy to find. Bursty noise, not so much.
There. You just start troubleshooting it. Like, you start looking halfway down to, the troubleshooting. What do we call it? Cutting it in half, or
divide and conquer.
Divide and conquer. But if it's impulsive, it's like, how do I find this? Or if it's being generated from a modem itself, and they only transmit when the modem transmits, how are you going to track that down? Like, I've had the ghost modems, right? We call it phantom traffic, where the modem's just transmitting whenever it wants, but it's not doing it during its actual time frame. Maybe time offsets are bad or something weird like that. Yeah, those are tough to track down.
Yeah. All right, so Sweet Lou is he's sweeping FDX amps up in North Jersey, and I'm down in Atlanta, so it's unlikely he's sweeping my amp.
Tell him to get a Dyson sweeper.
Yeah, they're faster. All right. So the next thing we want to cover is I picked section 6.3 out of the document because I wanted to cover two-way operation in the amplifiers. And a lot of people understand this, but not everyone. And this will lead us into the next section, which will make a lot of sense. So, a traditional amplifier, and I'm going to read this directly. So this all, folks, all this is just copy and pasted right from the document. So there's a lot of great information in this SCTE 294 document. So a traditional amplifier circuit amplifies in one direction, right? But we got two-way plants. So the solution: introduce two-way amplifiers to allow transmission of downstream signals, cable company to subscriber, in one frequency range, and upstream signals, that's the subscriber to the cable company, in a different frequency range. So two-way operation. Figure 4 shows a simplified block diagram of a two-way amplifier in which the green triangle represents circuitry to amplify downstream RF signals, and the blue triangle represents the circuitry to amplify upstream RF signals. So the things I want to point out for everyone on here is, in addition to that, there's a green triangle on here pointing to the right. That's amplifying your downstream signals from 50 megahertz to 1 gigahertz. Now it could be 1.2, 1.8 gigahertz. There's a blue triangle pointing to the left. That's amplifying your upstream signals, 5 megahertz to 42 megahertz. And as we increase our splits, that could go higher. But there's also a diplex filter on either side. And John, we've talked about the importance of diplex filters before. A diplex filter is a high-pass filter and a low-pass filter sandwiched together. And we see that in the boxes there's a box with an H. That's your high-pass side of your diplex filter, and another box with an L in it. That's the low pass filter of your diplex filter. And so if you're looking at the image, you can see an input and an output on each of those boxes. So the input comes in to the amplifier and it splits. The H goes to the downstream of your amplifier, and the L comes from the upstream of your amplifier. And that kind of combines it together. So it splits the signals apart in the amplifier so the downstream can be amplified and the upstream can be amplified. And then it combines them together, both on the input and the output of the amplifier. And at a high level, that's really how two-way amplification works in an RF amplifier. There's a lot of other signal conditioning that's in those blocks, but that's it, John.
Yeah, and the diplex filter. It's funny. I've had people say duplex filter, duplex. I'm like, that sounds like an apartment. It's a diplex filter, but you have to specify the split you want, and that's
Correct.
The problem we run into nowadays. Is what if I don't want to hard set my split? What if I want to go from 42 to an 85 upstream to a 202 upstream to a 396 to a 694 eventually? I tell other people, say DOCSIS 4.0, we talk about downstream speeds, but DOCSIS 4.0 came out because we need more upstream speed. And the only way to get that is to either run some super high modulation scheme in the spectrum we have or open up the spectrum. So we're trying to open up the upstream spectrum, so we need a diplex filter that's programmable, or get rid of the diplex filter. But there's a reason we have a diplex filter. It's so that signal doesn't bleed over from one side to the other.
Correct.
So there has to be isolation there that we can work with and design properly, because that signal makes a complete loop where it bleeds through the diplex filter, goes on the downstream, bleeds through the diplex filter, goes on the upstream, just keeps rotating around. We get a runaway oscillation. So then we end up creating our own signal in the amplifier itself, which is not what we want. And that's just the path, right? You also have just component to component, because the PC boards are so close that you could have signal leaking across circuits that aren't even connected. And that's where you come up with shielding and stuff like that, right?
Yes. And John, you mentioned runaway oscillation in an amplifier. Do you remember what we call a runaway oscillation in an amplifier from the SCTE 280 document? It's a specific type of impairment that we see in full band capture.
A signal generator? I don't know.
No, it's called a resonant peak. So
Oh,
if
yeah,
you
yeah.
have poor grounding in an RF amplifier, that's exactly what happens. You get a runaway oscillation, and it causes your signals to peak higher. So normally you'd have a nice flat spectrum in a full band capture signal. But if you have poor grounding in the amplifier, you get too much gain where you shouldn't have too much gain, or an oscillation, and you get a signal peak. So your signals will peak up at a certain frequency called a resonant peak.
I wouldn't call it poor grounding though. It's almost like poor design. I mean, you have more gain in that circular loop versus loss.
Yes. So
Right.
so there is in poor design, we compensate that by putting like finger stock on and an extra grounding in place, because after the PC board was designed, we realized we didn't have the grounding we needed, so we had to put this finger stock in place. And I say this is someone who designed RF amplifiers. But what can happen then is if you get corrosion on that finger stock, or you get corrosion between the actual amplifier module and what sits down into the amplifier housing, that corrosion degrades the grounding that you have between the housing and the amplifier module itself, and then you have oscillations that can occur. So kind of digressing here a little bit on the upstream troubleshooting, but trying to tie them together.
You remind me of the insurance commercial. We know a thing or two because we've seen a thing or two. We've been around. We're jaded. We've seen it all.
Been there, done that.
Yeah.
All right, so I wanted to talk about the two-way operation because I think it's important for people to understand that, and you touched on it. You talked about if we want to change that upstream to get more bandwidth, we have to change that diplex filter, because an amplifier may come with a diplex filter that has, say, a 42-54 split, as we say, which means the return path goes to 42 megahertz, and the forward path starts at 54 megahertz. So and John, you talked about this many times. A diplex filter has a limited crossover. So if my low pass side goes to 42 megahertz, my high frequency side starts at 54 megahertz, but I have like a certain gray zone here, or a dead zone, that is unusable, because that's the crossover region between my low pass and my high pass filter. So as we say, okay, now I need more speed in my return path, and the first logical step that most people look at is going to an 85 megahertz return. And when we do that, we'll move our downstream to 108 megahertz, and you'll see this gray zone gets a little bit wider than it was for a 42-54. Split.
Because of physics, electronics.
Yep.
The rule of thumb is about 25% of the highest upstream frequency. So if I go to 85, 25%, 1/4 of 85 is about 20, 21, 22 megahertz of no man land. So add 21 to 85, you get 108 or close to it.
Correct.
I remember when I was at Cisco, and Cisco bought SA, right, Scientific Atlanta, and the 85, it was really supposed to be 85-105 split, and they dropped it to like 85-104 or 102 or whatever it was, because Comcast and other people had millions of set-top boxes that they could frequency shift their downstream telemetry for the set-top box, but the lowest they could, or highest or lowest, was 105 or 107. So if you did an 85-108 split, it wouldn't work, because then your set-top boxes couldn't get their downstream signal.
Right.
So they squeezed it a little bit tighter, and the physics and still worked. So it was like an 85-103 split or 104 split. That way the downstream telemetry could still work at 104, 105, or whatever it was at.
Exactly.
Mm-hmm.
And so...
Yeah, right? There's two problems I see with diplex filter is, the more the upstream, the bigger the no man's land of the diplex filter because of that physics. And then anytime you have a diplex filter, you have group delay if you have signals near the roll-offs of the filters.
You got to stay, just as it is in the 42 megahertz, you have to stay away from that diplex filter, because, and Ron and I had talked about this, and in our last AMA, Ask Ron Anything, Ron talked about the issues, and he did a great job at describing the problems with group delay. So check out that last episode, a couple weeks ago, why signals have problems propagating and traveling when you put a DOCSIS channel too close to the diplex filter. It's going to cause issues with demodulating that.
Third problem I have with diplex filter is, what if you want to change the split later on?
Yes.
Right.
Well, it's why we get locked into it. And if ideally, if you're buying new equipment, you can buy equipment that has upgradable diplex filters, or as you mentioned, tunable diplex filters. So you could have one split today and you could change it later in the future. Unfortunately, the reality is a lot of cable operators have older equipment that the diplex filters are not replaceable, or even if they are replaceable, you have other circuitry in the amplifier that would need to be upgraded. So you have to change out the whole module. That's
even if you have a programmable diplex filter, you still on the downstream usually have an extra filter there, and on the upstream you have an extra filter in the upstream.
Yep.
In addition to the diplex filter, so they might have to be changed.
Right. Yeah. What I showed was a very simplified block diagram of an amplifier. As I mentioned, there's a lot of other signal conditioning in there and other filters that need to be changed. So it's not just a diplex filter. So So what are we doing here when we go to 85 megahertz, John? As you mentioned, we're starting to make the return a little bit more symmetrical to the forwards. We're getting more bandwidth in return. And that's been a complaint forever with DOCSIS. Is I can give you a lot of downstream speed, but I can't give you a lot of upstream speed. Now we're when we move to an 85 megahertz return, we can give more upstream speed. But let's look at the next step, and this is really where we're going with, DOCSIS 3.1 gives us the ability to go to a 204 megahertz return. So now our upstream and our downstream are getting much, much more symmetrical. When we look at DOCSIS 4.0, that upstream I think the sweet spot for DOCSIS 4.0 is a 396 megahertz return. You do get more bandwidth that you cannot use. The physics you mentioned is because as you get higher in frequency, the roll-off between your low-pass filter and high-pass filter gets wider and wider, so that no man's band gets wider and wider. But nevertheless, part of the DOCSIS 3.1 and DOCSIS 4.0 spec allows us to move our high end, our high frequency, higher and higher in spectrum. So with DOCSIS 3.1, we can go to 1.2 gigahertz. With DOCSIS 4.0, we're going to go to 1.8 gigahertz, with discussions about enabling us to go as high as 3 gigahertz. And if you're in a node plus zero architecture, 3 gigahertz might be something that we see in a not too distant future. And I think that's possible because that's something that we are already talking about. We had amps that at winter conference that could do 3 gigahertz, so they're out there.
Yeah, we have all of the other things we talk about too, though, the connectors and taps and drop cable and attenuation and blah 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 blah. Yeah, so we'll see if that comes to fruition. It's like we always say, it's like at some point you're like, why don't I just do fiber deeper? It's like there's going to be some type of trade-off. Eventually, you're like the bullet and rip it out and do fiber deeper, or I just go fiber to the curb and I just use drop cable. No more hardline cable.
Yeah, that
would be the depth that I could go with fiber. Right? Go to I always said turn the tap into an RPD, so you can have 8 customers off it, like an 8 customer service group, and then you just have drop cable. You don't have to worry about that last 100 feet and getting the right of ways and digging up people's yards and whatnot. But we'll see where things go. It all comes down to money. It's always money, right?
I mean, we are headed there as part of what we're doing with DOCSIS 4.0, and we're going to a lot of node plus 0 or even node plus 2 or node plus 4 architectures. And I really have the fiber node that's probably 100 feet from my house. I've got fiber 100 feet from my house to that node. So we are pushing, as an industry, we're pushing fiber deeper and deeper. It's just we know that running fiber to the house is the most expensive part. So we are a very fiber-rich industry. It's just we don't have fiber going to the home yet. It's eventually going to come. All right, so unity gain. Section 6.4.1 of the document goes into understanding unity gain. I cut a short section out of here. I didn't want to go deep into this because Ron Rannick and I have a whole session in our Back to Basics series that goes into understanding unity gain. But I wanted to point out that the SCTE 294 has several pages explaining unity gain both in the downstream and the upstream. So oftentimes we think of unity gain only in the upstream, but thanks to the session I did with Ron, even I came to realize that we do unity gain in the downstream as well. So the section I've highlighted here is the term unity gain is based on the fact that in a properly designed system, properly designed is the key word there, the loss in the cable and passive devices comprising the span immediately upstream from an amplifier is exactly offset by the gain of the amplifier, resulting in unity or no net gain. And then the figure below just shows, it's basically showing the sum of the amplifier's gain offset by the loss of the coax cable between the amplifier. And it's showing you as you go through the amplifier, the signal less the span of the cable is then amplified by the next amplifier. So you basically have unity gain. And if you look at the document here, again, I encourage everyone to download the document. The next couple of pages after this actually show numerically how you can calculate unity gain of each amplifier, and it goes into great detail of this. And John, I know you've done a lot of amplifier balancing yourself.
Yeah. And understanding, pre-stage, mid-stage equalizer pads. I find it ironic when you take a step back and because of physical spacing, where you put the amplifier in the pole, things are in the way. You try to design it properly, future-proof for spacing. But you buy the amplifiers generically with a set X amount of gain. So they're all the same, right? And you buy them. So if you take a step back and say, man, I put them where I could, and I had to balance them with a 5 pad here, a 10 pad here. Every pad you use, you waste the money.
Yep.
You pay for gain, and
you're throwing them away.
So I like this idea of the new smarter amps that have no pads and EQs. They're kind of they're biased electronically, smart amps and all that. But the EQ, there's nothing really you can do about it. You're going to have some type of maybe smart equalization. But if you could bias the current to the hybrid itself to change the gain stage, you wouldn't have to put a pad in. And if you change the gain stage to be lower because you don't need it, because you're going to pad it anyway, you have less power draw.
Yep.
So you're saving money, right? And then if you need it later on because you're going to extend your spectrum, then you could jack it back up again. Because more spectrum means more loss in coax, means you need more gain to be able to push the signal further. So it's kind of a cool idea to maybe get away from pads if I could. Now, if I could design a plant perfectly, they would be spaced out with 0 pad everywhere. And I know I wouldn't waste money.
Alternatively, if you're putting 10 and 20 pads, 10 and 20 dB pads in your amplifier, you might want to check the amplifier, or you might want to talk to the guys who designed the plant and figure out why you're throwing away so much money in loss, because that is a non-optimal design.
It's funny. We used to use 20 pads as like Terminators.
Yeah.
20 dB. And if you do the math, logarithms, every 3 dB's, double power.
Half the power. Or double the power.
100 times.
It's a lot of lost power.
Yeah, it's crazy. But we live with what we got, and it's like you're dictated by the actual geography and what you deal with outside, right?
Yeah. All right. So everything in the document so far has really been a setup for Section 7. And Section 7 in the document is about all the types of impairments that you're going to find on the upstream in a network. And I've cherry-picked a couple of the impairments that I like, that I think are a little atypical. And one of them that I found is really unique is this one on drop amplifiers, or also called subscriber amplifiers. So drop amps, inclusive of above-mentioned devices, will have many of the same failure mechanisms observed by their larger cousins, by regular amplifiers. So why do we have drop amplifiers? Drop amplifiers are typically purchased by homeowners, or could be by, also used in apartment buildings to, for whatever reason, increase the gain within a subscriber's home. So maybe you buy this because you want to move the modem to a different location in your house, and you're going to add some coax cable in your house. Or maybe you buy it because you think the signals that you're receiving in your home are too low from your cable provider, and you're going to buy this drop amplifier and pull it in. Or maybe even a cable operator puts it in because you have a bunch of TVs in your house and you need this additional gain. But it's like a mini amplifier that's hanging out on the pole. It has a diplex filter on each side. That diplex filter is going to have a fixed frequency, like 4252, or 42 megahertz on the low side and a 52 megahertz on the high side. And it also has amplification in it and things like that. So any problem that can happen with an outside amplifier can also happen with these. What I'm showing with this amplifier is for a cable operator who has upgraded their plan from 42 megahertz to an 85 megahertz return. And one of their SC QAMs, the one that's circled in red on the right-hand side, we're showing the channel response to that. And that channel response of the SC QAM, it just looks like a vertical line going off the screen. The rest of the channel responses of the SC QAM, they're within the green band. So we're looking at the pre-equalizer channel response. We also call this ICFR, in-channel frequency response. Cable Labs wants us to start calling this just channel or frequency response or channel response now. But it's that last channel that's problematic. And I'll let you talk about why one channel can be problematic, John. Maybe you can explain that. But that channel is off the chart because it's all the way up against the diplex filter of the drop amp inside the subscriber's house. So it's trying to pre-equalize and compensate for the roll-off zone of the diplex filter. So it's hitting that diplex filter hard. And John, what do you think? What kind of problems could that cause?
It's probably not going to work. This is a big concern because the modem and CMTS can negotiate and talk to each other, and there are TLVs, CM status messages, and information from a cable modem to tell a CMTS, here are my capabilities, here's what I can do. And then the CMTS and cable modem can say, hey, don't even lock on that channel, don't range on it, don't even use it, because you told me you're a 42 megahertz modem. But the drop amp has no smarts to it. The CMTS and cable modem have no idea there's a drop amp, so there's no communication there. So the CMTS and cable modem say, hey, I'm an 85 megahertz system, let's do it. So it tries to
let's rock and roll.
And it can't. The pre-equalization in the modem is trying to compensate as much as it can, so it's railed out, and then it just never works. So now if I were on the CMTS and I configured a 5-channel bonding group with that one channel in it, it's probably not going to work at all. Now, if I had a 4-channel bonding group created, it would fail on that one channel and say, hey, I still have a 4-channel bonding group I could use.
Right.
So that modem there could end up in single-channel upstream mode. And you're trying to sell them 50 megabits per second on the upstream, and you're only getting 10. So, yeah, it could exacerbate the issue. And that's why it's, you mentioned that drop amp. What's worse than that is if it's just downstream only and the upstream's passive.
Right.
So there's no gain at all in the upstream, so it's even worse.
And that depends on the drop amps that you buy. Some have gain only in the downstream, passive on the upstream. So,
and most people just care about the downstream because they're just looking at downstream signals.
Correct.
They don't think about their upstream. Yeah. So that is definitely a concern. And then especially when we go to DOCSIS 3.1 with OFDMA, you're like traversing that spectrum roll-off where half of the OFDMA is on this side of the spectrum and half is on this side. And it could be a mess.
And I know when we were working on this document, one of the guys was from Europe that was working on it. He says some of the European drop amplifiers have like noise suppression in them. So on the returns, so they will limit. They'll basically cut off until they get enough energy to turn them on. So it keeps the noise out of the return path. I haven't seen these in the US, but apparently they're in Europe. And that causes problems if you're running OFDMA only, because you need enough noise, enough energy to turn them on. And that's kind of like the RFOG problem. If you don't have enough energy to turn them on, like for OFDMA, then that OFDMA signal doesn't even get through the drop amp. So
Yeah, at the time they were
those are,
called like dynamic ingress blockers.
yeah, I think that's what it was.
Like
Yes.
yeah,
Yeah.
which was a cool idea. So it's kind of like it would get rid of the noise funneling effect because you basically shut everyone off until the modem's ready to transmit. Because everything on the upstream is bursty. So if you had noise in your house, it really only came through the upstream when your filter opened up.
Correct.
But like you said, it could have its own problems, and it's like putting a Band-Aid on a problem, right? You're instead of fixing the ingress and the problems, you're trying to block it when you can, and then what happens if that filter doesn't work? Yeah.
Exactly. All right, the next one I liked is a type of impulse noise. So we said, if the noise was continuously there, it's easy to find. The more difficult one is the example that I'm showing on the screen here. So this is a return path spectrum analyzer. This screenshot's from a Viavi analyzer, and I think they're using the UTSC type of analyzer here. But what we see is a lot of really noisy signals, not just at the low spectrum, like at 5 megahertz, but we see this all the way up to 42 megahertz. And that's basically, it's a 42 megahertz return, so it's getting cut off there. This is coming from subscribers' homes. And we really started to see this type of impulse noise with the advent of LED lights, and specifically high-level LED lights that were used in grow lights. The two first states that we saw a lot of this in was in California and Denver when marijuana was legalized for growing, and then this started to show up significantly when large operations became active. So this was injecting substantial amounts of noise. Now this has proliferated a lot. When there was a specific signature for like sodium lights, but it was limited in frequency. Now with LED lights, fluorescent lights, also street lights, and as more and more street lighting are going to LED, we're seeing this very broad signature coming into the return. So it's something for technicians to be aware of if you have any type of shielding that is compromised, a loose connector, a poorly terminated F connector that's near any of these grow lights or any of it's not so much the lights as it is the power supply that's going into the lights, because a very high frequency switching power supply that provides power to these lights. You're going to see a lot of this noise coming in. You got to track it down. You're not really going to be able to have people turn off their lights, but you can ensure that you clean up the shielding integrity on all of your coax lines, and that will mitigate it.
You can't just go around and smell for skunk weed.
Well, that may lead you to the source of the lights.
Do I bring my dog with me?
Yeah. B. Garin 444. That's a great question. He says, when you have higher ICFRs, say over 3 dB, what problems can you expect to see? So he's talking about the pre-equalizer compensating for impairments. Generally, the rule of thumb is that when your channel response or your in-channel frequency response is greater than 3 dB, that almost indicates, that typically indicates an in-house problem. By in-house problem, something at the drop or in-home wiring associated with that modem. And the reason I say generally that it's greater than 3 dB, we associate that with in-home wiring, is outside plant problems tend to, they can manifest channel responses that are 3 dB or less. And that's just based on what we've seen, observations. So the large channel responses, greater than 3 dB, those are generally going to be in-home issues, drop-related issues. Less than 3 dB channel response are going to be outside plant issues. Great question, though.
Yeah. I mean, I would say that your bottom line really is like you look for uncorrectable effect, nothing there. But you look at your upstream MER, and the pre-equalization is probably taking care of that 3 dB in-channel frequency response, but you're eating into your pre-equalization. So your pre-EQ has a finite amount of capability. So if you're already using most of it to take care of an in-house problem, what happens if that signal sees a micro reflection in the plant itself? that might put it over the edge, and now the MER is really bad and doesn't work.
Correct.
So it's like, yes, we do have some Band-Aids in the system to take care of it, called pre-equalization and all that, but you don't want to use it all up on something you should fix in the first place or avoid, Yep. That's my take anyway.
So Dominic asks another great question. He says, can coax or QAM go up to 3,000 megahertz, which would be 3 gigahertz for either internet or linear TV? So I'll break that up into two parts. QAM can be, so QAM is basically quadrature amplitude modulation. That's basically a baseband concept. And QAM gets modulated. So you take your QAM, your quadrature amplitude modulated channel, and you upconvert that. And we can upconvert that to any frequency we want, even up to light, because we take our QAM channels and we put them on a fiber optic cable, which is operating at terahertz. So yes, QAM could go 3 gigahertz, 60 gigahertz, or 6 terahertz if we wanted to. It can be transmitted over light. Coax, and I apologize, I'm getting a little raspy here.
That's the problem, is the coax has more attenuation at higher frequencies. So to go to 3 gigahertz, our coax might not have been specified out there. We have known suck
it depends.
Out, fall off. Yeah, it depends. The connectors themselves, the craftsmanship, the taps, the amplifiers. There's so many components from end to end that you don't know. They're usually specified for 1 gigahertz or 1.2 gigahertz. Now we're looking at 1.8 gigahertz. But to go to 3 gigahertz, the coax could probably handle it.
Good coaxial cable could go much higher than 3 gigahertz.
Yeah, it's just the fact that it won't go as far, before it drops really low in level.
Yep.
There's more attenuation.
LC says, can over 1 dB ICFR, or channel responses, we're saying, on all frequencies at a tap affect modems? Well, that's a big depends again. I mean, 1 dB is really not that bad on your ICFR. However, depending on what other things are happening with the modem, I would say generally over 1 dB, that's not too bad. But if it's a 1 dB sinusoidal wave, then that's probably giving you indication that you have something maybe in the outside plant that is damaged. And if that's causing uncorrectable code word errors, or if it's causing too much group delay or something like that, we really have to look at what is underneath the impairment that's underneath there to determine if that's actually subscriber impacting or not subscriber impacting.
It's Chicken Little. Don't ever scream the sky is falling when a dB between friends is no big deal.
Exactly.
I'm not going to squabble over a dB because the accuracy of test equipment could be a dB or two.
Exactly.
So it's like, I'm not going to worry too much about something like that. It's funny how, you look at a spectrum analysis trace or a sweep trace. If I did 10 dB per division, everything looks flat. But if you do 1 dB per division, everything's magnified. It looks really bad, but you got to put it back into context. If I'm looking at 1 dB per division, it's nothing.
And Dominic says, did the head ends do the C-band reallocation since we don't have 200, he follows up to say 200 megahertz left for the end satellite dishes at the head end? And I don't know the question to that, John, or the answer to that, John.
I don't know the question either. What was the question?
I think he's talking about, maybe he's talking about reconverting the MPEG down for DOCSIS, but I'm just not sure. So maybe he can follow up on that. Let's jump into the next slide because we're running really short on time here. I want to jump through these. So CPD was in the document, and I wanted to touch on this because most people who are familiar with, it talks about third order CPD composite. Wow, I'm blanking on CPD.
So let's back up. Common path distortion.
Common path distortion, thank you.
This is distortion that's created in the common path. So it's not created on the high side in the amplifier or the low side in the amplifier. It's on the common path.
Right.
Seizure screw, tap, any place where upstream and downstream signal exist together. The common path.
CPD occurs when the downstream RF signals pass through a diode-like nonlinearity, and then they show up on the upstream, on the return path. And a lot of times, folks who are familiar with CPD from analog days, they're used to seeing CPD spikes on a return path analyzer every 6 megahertz. And what I wanted to point out from the SCTE 294 document, since we're going to all the signals in a downstream are like 6 megahertz blocks or 6 megahertz wide, or now we're going to OFDM channels, which could be up to 190 megahertz wide in a downstream. When you have CPD on your upstream, you're not going to see those 6 megahertz spikes. It's just going to look like an elevated noise floor. So this is what CPD looks like today if most of your channels in the downstream are all QAM channels or are all OFDM channels. So that's a change for people. But if you've never seen CPD before, this is what CPD looks like if you have it. It's a very elevated noise floor. And what we're looking for, like you said, John, this is a downstream issue that manifests on the upstream. You can go and rattle an amplifier, and if that noise goes away, or even opening the lid on an amplifier or a passive device, and you see that noise floor drops, you know you found the source of your CPD.
Yeah, the simple math and a quick explanation was channel 3 is at 61.25, video carrier. Channel 2 at 55.25, the video carrier. Take those two video carriers, one minus the other is 6 megahertz.
Yes.
So it's just the mixing of those two downstream video carriers, and the mixing of the two creates a 6 megahertz carrier. Well, that falls at 6 megahertz. So that's why you see these downstream signals intermixing, creating artifacts that fall at 6, 12, 18, blah, 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 blah. But now you don't have video carriers on the downstream. Discernible, discrete, coherent carriers every 6 megahertz. You got a chunk of noise. 6 megahertz or maybe 192 megahertz of OFDM. You mix that with a block of OFDM lower down, you get the
more noise.
The minuses, all over the place. So not only do you get CPD, elevated noise floor in the upstream, if you do the math, you'd have an elevated floor in the downstream as well. Because you get F1 plus or minus F2, F2 plus or minus F3, F1 plus F2 plus F3. We're always assuming CPD is F2 minus F1.
Correct.
So we get a lower result, right? In the mathematics.
It still just looks like noise.
Yeah, but you could have the addition of frequencies, and that addition of noise is not going to fall in the lower frequencies. It's going to fall in the higher end. So, yeah, you're going to have a higher noise floor in the whole spectrum, not just the upstream.
Yep, indeed. All right, so Dominic came back. He said, it's the 5G reallocation that took that satellite frequency. We used to have 500 megahertz full. It was 5G that took it. Okay, so I see what he's saying. It's the telephone company. So they've reallocated the frequency spectrum. And he's saying, so did the head ends do the bandwidth reallocation since we don't have that megahertz left?
It sounds like what we did with over-the-air digital, right?
Yes.
We took our analog channel 3 that used to, we would carry it, and then the broadcasters went digital, and they're like, oh, we're going to do PBS at 400 megahertz now at UHF or whatever. So there was reallocation of spectrum. So the government could raise more money. They auctioned off the spectrum, right? But I mean, and I think, Dominic, you realize we're an enclosed cable network, so we can put it anywhere we want. Right. I think he's talking more about over the air.
Yeah, and I haven't been I don't Ron Randick would probably know the answer to this. I have not been following the over air spectrum as much as I have been the wired spectrum. So shame on me, Dominic. I apologize. I don't have an answer for you there.
We were called cable for a reason.
The cable guys. So just a couple more slides here to go. This next one is just for people that are, when you get up to 85 megahertz, you're not going to see an 85 megahertz return. You're not going to see all that much additional noise. There is an IF frequency on television sets around 44 megahertz. But when you start to go to a 204 megahertz return, guess what? You're going to start overwalking the FM radio band. It definitely, if you're in North America, South America, even in Europe, you're probably going to start to see that come in. And what I have highlighted on the screen here in the box in red is a 204 megahertz return. You see, this is a production system, by the way. You see a number of SC QAMs and OFDM band, and then that red box is showing the FM band leaking into the cable plant on the upstream. So that is going to be an interfere, and that's something that your operators are going to be want to be aware of. If you're going to want to put an OFDMA channel there, you either going to want to put an exclusion band around there, around the FM band, or ideally you want to use PMA, Profile Management Application, because that can adapt your OFDMA channel to allow your modems to use that frequency without much impairments.
It's kind of like why punish all my end users by avoiding it when maybe I can just punish the people that have the problem.
Yes.
And so some people might run at 1024 QAM in the upstream, and other people is like they're relegated to 256 QAM because they do have FM ingress on their side of the plant, or it only pops up when they're transmitting. Who knows, right?
Indeed. B. Garrett asks, he said, one last question about ICFR. Can ICFR backfeed from the customer drop or house wire when checking at the tap? So it doesn't backfeed, but you can have like either bad wiring in your house can impact the modem's transmit, pre-equalizer transmit, and can impact your ICFR, or your neighbor. If you're on a low value tap, like a 4-value tap, an 8-value tap, impairments at your neighbor's house can impact the house that you're checking and can cause problems. I always have called that like neighbor near neighbor impact. So yes, it's not necessarily backfeed, but it's isolation problems. So one neighbor can impact another, or in-home wiring can impact that subscriber's ICFR. All right, so a sampling of what we didn't have time to cover that was in the document. There's the SCTE 294 covers a lot with impulse and burst noise, narrowband signals, switching regulator noise, return path amplifier distortion, HPNA, OBI, optical beat interference, and more. It covers a lot. I just want to give you guys a sampling of some of the cool things that are in the document. Highly recommend downloading the document. Section 9 in the document covers measurement and troubleshooting. So it starts off with how to use a regular spectrum analyzer, but these days, upstream triggered spectrum capture, UTSC, which is integrated in some, I would say most CMTSs and DAA nodes at this point, can provide some, but not all, benefits of standalone spectrum analyzer. And we saw that on the previous slide. That was that spectrum analyzer screenshot was an example of UTSC, the upstream triggered spectrum capture. So it gives you great insight into the upstream. And don't forget the appendix. There's a great appendix in SCTE 294 that shows you how to calculate total power and some other things that are very interesting. So, in DOCSIS 3.1, we've all gone to 1.6 megahertz power calculations. So there's some, how do you do that power calculations? Very important. And John and I, we've covered that before. Things have changed in how we do upstream power calculations. So that's an important thing for folks to understand as well. And that is the end. One last thing here. I did have links on the slide for people. So thanks for all the authors who worked on the SCTE 294. I think it's a great reference. I have a link. I have the full link there for the SCTE where you can download it, a bit.ly short link. So if you go to bit.ly/SCTE 294, that'll give you a link to download the document, or if you take a screenshot of the QR code, that'll take you directly to the document so you can download it. Again, it's great reading, great document. So that's what I wanted to cover today, and definitely hit that like and subscribe button if you enjoyed the content, folks. John, what do you think of that document?
Yeah, it's in depth. I mean, there's a lot of information there, and we keep saying that it'd be good to have all this information in one spot. It's funny, it's taken us this long to get stuff like this together, right? A lot of it's just passed down from person to person and on-the-job training. Talk to Ron, you get that information. We got stuff from Jim Coons and
Yes.
the guys from 30 years ago. But yeah, putting that all in one document, I think makes sense. And then we can easily search things better too. Once it's written down, you can Google search stuff and it'll find keywords that you're looking for. You type in impulse noise and maybe pull up 5 different documents.
That has been a big challenge. So much of what we have in the cable industry has been tribal knowledge, and now we're trying to work and put them into documents so that when we all retire, it will be documented.
I like that word, tribal knowledge. We're like cavemen.
So thank you so much, John. I appreciate your insight. Thank you to everyone in the chat room for your discussion. We had some great questions during this. We hope everyone found the episode on SCTE 294, Understanding Troubleshooting Cable Spectrum or Cable Upstream RF Spectrum, was an insightful document. I thought it was a great document, John. I hope you also enjoyed it as well. We covered a lot of great topics. If you want to dive even deeper, be sure to check out the full SCTE 294 document. It is packed full with great examples, diagrams, and expert guidance straight from SCTE and Cable Labs teams. I will include the link in the description, the YouTube link in the description below. Huge thank you again to my legendary co-host, John Downey, and also for my producer, Mia Calabrese, who always brings the fire to our shows. Thanks for tuning in, everyone, with great questions and being part of the cable tech community. Don't forget to like, subscribe, and hit the bell so you never miss a great episode of Get Your Tech On. We'll be back next time with more DOCSIS deep dives. Until then, take care, everyone. So long.
Adios. Sayonara.